what we're excited about it is potential, hopefully leads down the path of a prevention for SUDEP.
Fellow Homo sapiens, welcome back to Epilepsy Sparks Insights, and actually our first episode of 2024. We don't mess around, so today we are chatting to epilepsy neurosurgeon Brian Dlouhy about his research into how SUDEP, or sudden unexpected death in epilepsy, could be caused by a brain not feeling air hunger or the need to breathe following amygdala seizures. So rather than SUDEP being potentially caused by cardiac issues, maybe it's respiratory dysfunction. A quick one, please don't forget to like, comment and subscribe, because your comment and like will help spread awareness and understanding of the epilepsies around the world. Now, on to our start of the week, Brian Dlouhy.
My name is Brian Dlouhy. I am a neurosurgeon and a scientist as well, researcher, currently at the University of Iowa, associate professor there. I did my medical school training at NYU, New York University School of Medicine. Then I went to the University of Iowa for my residency in neurosurgery. I did a post-doctoral fellowship there in epilepsy, where I started focusing on understanding SUDEP and how the brain controls breathing. And I did a focused fellowship in pediatric neurosurgery, so I do mostly pediatric neurosurgery, and I have a clinical interest in pediatric epilepsy surgery, and then again my research is mostly epilepsy and SUDEP.
And what led you to this sphere? SUDEP is something that often scares a lot of people. I think we should all be talking about it, but tell us what led you to that part of the epilepsies.
I've always been interested in research, in understanding how the brain functions, and I just kind of followed the science. And the data that I was gathering, I was actually working on emotion and fear and panic and anxiety, and understanding how the brain processes that and how we as humans integrate, and how what areas of the brain then kind of control those perceptions that we have, and those really in those conditions, those disorders. And that led me down a path of looking at breathing control, and then I kind of combined that with human data and epilepsy, and it all just kind of, we came to this hypothesis, all kind of together, kind of serendipity, and this hypothesis that there may be areas in the brain that control breathing during seizures, and that's what leads to apnea during seizures, and then SUDEP.
So your recent paper, I believe it's the one, failure to breathe persists without air hunger or alarm following amygdala seizures.
Yeah, that's it.
Perfect. Tell us about that, because I honestly, this is complete coincidence. I was talking to somebody else about SUDEP and breathing or not breathing at the same time. So this comes at like a really cool moment for myself. But tell us about your work and what you discovered in this. We've
been working on this, I would say, for and we have, this is our third kind of paper in a row on this, probably the last decade, the last 10 years. A lot of data came out like kind of early 2010s that suggested that, SUDEP was probably more respiratory, dysfunction after a seizure or during a seizure, rather than cardiac. But the mechanisms, underlying how a seizure causes loss of breathing were really unknown. And so then we started studying our epilepsy patients, right? So we studied them, and we're studying my surgical patients. These are the patients that get implanted with electrodes to identify their seizure focus. And the goal there was to record their seizure activity and record their breathing at the same time they're having seizures. And at the same time that we're going to functionally map their brain by electrically stimulating different parts of the brain to understand what their motor system is, their sensory system, and their respiratory system, what controls breathing. And interestingly, we found that when seizures spread to the amygdala, or when we electrically stimulate, and it's a specific site in the amygdala, not the whole amygdala, and that's key, then patients will stop breathing. Really, we had no understanding of how this kind of occurred before that. It was thought that maybe, seizures somehow, affected the brainstem, but really how they did that was really unknown. So the amygdala seemed to be that kind of key structure. Interestingly, and over time, I thought that there'd be many other sites, and we'd be able to kind of create this respiratory kind of homunculus or network in the brain, and there'd be many sites that would inhibit breathing, but we've only really found this specific area in the amygdala so far to date. Now, there may be other structures, but that's where we're kind of honing in on, just because it seems to be such a critical structure and such have a potent ability to inhibit breathing in humans. So we've done this in adults. We have it then. We did this in even a person without epilepsy. So this function of the amygdala is probably in all of us. And we all have this, the amygdala in all of us probably inhibits breathing, and for different purposes, physiological purposes. But seizures hijack that area then to cause apnea during seizures. And so we did that in adults, we've done that in kids, again, patients without epilepsy. We've all found the same effect. We've done this now as young as 2 years of age, and even different epileptic syndromes, tuberous sclerosis, all different types of epilepsy, and temporal lobe epilepsy, frontal lobe epilepsy, generalized epilepsy, so forth. Our latest paper, and what was so novel about it and what we're excited about it, is potential, hopefully leads down the path of a prevention for SUDEP in patients with intractable epilepsy, is this finding that in some patients, when seizures spread to the amygdala, they not only have apnea during a seizure, but that apnea then persists even after the seizure ends. And it can persist for even up to 15 minutes in what we saw in some patients. We'll have intermittent breaths, but in between these breaths might be 20 seconds of apnea, right? And in the patients that we studied, right, there are 5 out of 20 that we found this effect. There'll be this apnea as it almost gets longer and longer and longer after the seizure. And then in these patients, then if they're able to recover, and you can see this kind of slow recovery where they start breathing a little bit more and a little bit more regular, and then finally they just they take off and then become regular again. And it varied kind of on the timing in different patients. Interestingly, we could also stimulate the amygdala and even a smaller site in the amygdala and find a similar effect in 5 of the 20 patients, where when we stimulate, they'd cause apnea, but then the apnea then would persist even longer after the stimulation ended. So that was helpful because it really kind of pinpointed this amygdala site, and we could map it, and we find what nuclei are in the human amygdala that are involved in this circuit. And interestingly, in all of these patients that we studied, they're not aware that they've stopped breathing, and we think that's part of this really kind of critical. Part of the critical mechanism underlying SUDEP is that not only do seizures spread to the amygdala and cause loss of breathing or apnea, but it also inhibits that amygdala structure, is inhibiting that air hunger that you would typically have with such loss of breathing, right? Most people, if you hold your breath for even just a couple of seconds, you're aware of it. These patients, they're completely unaware of it. So it's that kind of, they're not, and SUDEP is that thing where people are, they die alone in bed. It's that scary phenomena of just there's no alarm bells that go off, right? No one's alerted. Everyone's like, well, geez, how did this happen? There's no, we didn't know. I mean, no one, there was no cry for help, right? And that's because that those alarm bells aren't going off in the individual. And so we think it's like this 2-hit hypothesis. That's what we have, this 2-hit hypothesis that occurs that ultimately then leads to SUDEP. So hopefully, we've been able to kind of map this circuit to the brainstem using the unique tools like imaging in the MRI scanner while we stimulate the brain, electrically stimulate the amygdala. And so you can find this circuit. We've been able to kind of tease out mechanistically what areas of the brainstem we think are affected and that control breathing by studying patients in the operating room as well. And we find that, there's this site, that site in the amygdala also can inhibit breathing, but also appears to inhibit like this chemosensory function that controls breathing as well. So we think that it's inhibiting like multiple pathways in breathing control, as well as our ability to sense breathing. So it's also inhibiting kind of the interoception, our internal sensation and integration of breathing signals up to the brain to tell us, hey, look, we're not breathing normally, or we're not breathing at all, do something different. So we think that these patients that have this kind of more persistent loss of breathing and that persistent kind of loss of the air hunger are the ones that are probably higher risk of SUDEP.
And do we know why these people might have less of that hunger? Could it be a genetic thing or what? Do you know? So
that's the question. Why do some patients, I guess in general, because only 5 of the 20, right? Everyone has this apnea when we stimulate the amygdala. Everyone has apnea when seizures go to the amygdala. Why is it that in some patients it persists, right? It puts them at higher risk. And we think that this is some kind of epileptogenesis, repeated seizures that are changing the networks in the amygdala, in that circuit from the amygdala to the brainstem, that plays a role in that inhibition of breathing, as well as the other circuits that go to other parts of the brain, like the insula, which are involved in air hunger. So we think that these patients they may have a genetic risk factor for this as well. And maybe the types of seizures they've had, and that also may play a role, right? So some genetic components. There's this other component where probably repeated seizures also has a role in changing this network and the structure in the amygdala. But that network to the brainstem, we think, is kind of critical.
Does this kind of mean that perhaps if the longer a person has refractory epilepsy, potentially the higher their risk of SUDEP may be? The
data would bear that out too in the literature. We see that, right? So it's intractable epilepsy patients. And you will see this occasionally, first time seizure, or even like we haven't had a seizure in a long time and they have that. So there may be some other, components to it that we don't understand just yet, but some genetic components. And there's definitely an environmental component, right? We patients are in bed invariably, right? It's at nighttime, right? In bed, and they're found face down, prone in bed. So there's other environmental components as well. People aren't dying from SUDEP, right? Out in public, for example, right? The thought there, obviously, someone has a seizure in public, they get help, right? And that's witnessed. And so that's the key there. But alone in bed, there's that the person's by themselves, so then there's no alarm. They have no alarm going off, right? That their breathing's changed. And there may be other roles of the sleep that makes breathing more dependent on different mechanisms that are really inhibited from that seizure.
So what are next steps in your research? You have collated this excellent information, all this data, and come to these conclusions, but what are your next steps?
We want to better understand the circuit as well, from the amygdala to the brainstem. We also want to really kind of test the hypothesis that the amygdala, right, is really critical for this pathway and for SUDEP. And so, doing things like ablation in the amygdala and then seeing if that affects breathing after a seizure, and see if it stops that seizure-induced apnea or the persistent apnea after a seizure ends. And so that's one area that we're exploring and we're very excited about. One other thing is that we're interested in looking at using this as a biomarker too. We want to develop a platform where we can use different tools, investigations, whether it's respiratory measures just at the bedside or an outpatient clinical setting, as well as imaging tools like MRI or functional imaging, as well as then possible mapping of the brain to create a risk profile, as well as then the clinical demographics of patients. Combine all it together into like to identify patients that are high risk, right? So we create this risk profile for patients to say, this patient seems to be at high risk, so everyone with epilepsy could undergo this, right? And they could put them into this kind of clinical kind of profile. I think, if you have epilepsy, if you have intractable epilepsy, you're afraid of SUDEP. I think rightfully so, right? And it's and trying to alleviate some of that concern and it would be very helpful. And then also, by saying, hey, you're lower risk, you're less concerned. I think that would help people, number one. I think identifying patients at high risk then would say, hey, look, you're high risk, hey, we are trying to develop some preventative strategies, I think, therapeutically to prevent SUDEP in patients. And, I think those are the things that we're thinking of. And could those patients then enroll maybe in a clinical trial or something that we're interested in doing in the future? And by identifying the high-risk patients, then we identify that patient population that may consider something like that.
Thank you to Brian for researching SUDEP causes and helping so many of us with epilepsy to have hope for the future when it comes to further minimising SUDEP risk. Again, if you haven't already, don't forget to like, comment and subscribe, and see you next time.